Tonight, we're going to look at the most consequential number in the history of the sky. Not the size of the universe, and not the age of it. The rate at which the universe builds stars, and the fact that this rate reached its highest value billions of years before the Earth existed, and has been falling ever since. For the first 3.5 billion years after the Big Bang, the rate went up. Gas cooled, collected, and collapsed, and across every cubic megaparsec of space, the universe was assembling new stars faster each 100 million years than it had the 100 million years before. Then the climb stopped. It held near its maximum for a while, the way a tide holds at the top before it turns. And then it began to fall. And it has been falling for roughly 10 billion years, and every step down has been permanent. That is the part worth sitting with. Not that the rate declined, but that the decline removed things one at a time and did not give them back. The era when a typical galaxy could build 100 solar masses of new stars every year is over. The era when cold gas fell freely onto young disks is over. The era when the sky was crowded with galaxies close enough to disturb each other into bursts of construction is over. Each of those thresholds closed quietly, and none of them reopened, and none of them will. There will never be another cosmic noon. Not for us, and not for anyone who comes after us. Anywhere. So the question is not whether the universe is still making stars. It is. Tonight, somewhere in the disk of our own galaxy, a cold clump of gas is crossing the line where gravity beats pressure, and in 100,000 years there will be a star there that does not exist yet. The question is what it means that the great construction is behind us. If most of the building is already done, what exactly is a night sky? Is it a work in progress, or is it a finished room that we happen to be standing in? By the end of tonight, you're going to understand exactly 3 things. You will understand how astronomers weighed the star making of an entire universe, using light from galaxies so distant that the measurement is really a form of archaeology. You will understand why the rate collapsed to roughly 1/9 of what it once was, and which specific supply lines closed to make that happen. And you will understand the strangest consequence of the whole story, which is that even though the factory is winding down, nearly every star it ever built is still burning right now, above the roof you are sitting under. Before we get started, if you love exploring the deep history of the universe as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what the measurement actually is, because it is not obvious that it is possible at all. We are used to measurements of single things: the mass of Jupiter, the distance to Proxima Centauri, the temperature at the center of the sun. Those are hard numbers, but they are bounded numbers. There is one Jupiter. You measure it once carefully, and you are finished. The cosmic star formation rate is a different kind of quantity. It is not a property of an object. It is a property of everything at once. The number astronomers want is this: across the whole universe, in a given amount of time, how much new stellar material is coming into existence. Not in one galaxy, in all of them, averaged together, treated as a single system. To make that meaningful, you have to divide out the expansion of space, because the universe keeps getting larger, and a raw total would rise or fall for reasons that have nothing to do with star formation. So the quantity is defined per unit of comoving volume. a volume that stretches along with the expansion and therefore contains the same galaxies at every epoch. The standard unit is solar masses per year per cubic megaparsec. A megaparsec is about 3.26 million light years, so a cubic megaparsec is a generous box, large enough to hold the Milky Way and Andromeda with room left over. Inside a box that size, right now, the universe converts about 15,000th of a solar mass of gas into new stars every year. That number is small in a way that is easy to misread. It does not mean the universe is nearly finished. It means the accounting unit is enormous and the process is slow. A cubic megaparsec is a big enough region to hold roughly 100 galaxies of assorted sizes, and in a year, all of them together produce a bit less than 1/60th of the mass of the sun in the new stars. Stretch that out to 1,000,000 years and you get 15,000 solar masses, which is a respectable cluster. Cosmic processes look tiny per year and enormous per epoch. That is simply what happens when you divide a very large thing by a very short time. The reason this quantity matters more than almost anything else in extragalactic astronomy is that it is a ledger of production. Every heavy atom in your body was assembled inside a star, released by that star's death, and mixed into gas that later made another star and, eventually, a planet. The rate at which the universe made stars is therefore the rate at which it made carbon, oxygen, iron, and every other element that is not hydrogen or helium. It is the rate at which it made the conditions for chemistry. Trace that curve and you have traced the manufacturing history of everything solid. So the goal is a graph. On one axis, cosmic time from a few 100,000,000 years after the Big Bang to the present. On the other, the rate. And the shape of that graph is the entire story. The remarkable thing is that we have it. Not perfectly, not without argument at the edges, but we have it, a measured curve, built out of hundreds of surveys that tells you what the universe was doing at every stage of its life. It took about 30 years of work by a large number of people to draw. And what it shows is that the peak is behind us. Before going further, one piece of vocabulary needs to be made concrete because everything tonight is measured in it. Redshift. The number that keeps appearing, Redshift 2, Redshift 1.3, Redshift 0.7, is not a distance and it is not a time. It is a measurement of how much the universe has expanded since the light left. Here is the mechanism. Space itself stretches as the universe expands. A photon traveling through that stretching space has its wavelength stretched with it in exact proportion. If the universe has doubled in size since a photon set out, that photon arrives with twice the wavelength it started with. Light that left as blue arrives as red, and light that left as red arrives as infrared. Redshift is defined so that the wavelength ratio is 1 plus the redshift. A galaxy at redshift 1 is seen by light that left when the universe was half its present size. Redshift 2 means 1/3 the present size. Redshift 9 means 1/10. That is a very clean measurement to make because atoms produce spectral lines at fixed, laboratory-known wavelengths. Find the pattern of hydrogen or oxygen lines in a galaxy spectrum. See how far the whole pattern has shifted toward longer wavelengths, and you have the expansion factor directly. No assumptions about brightness, no distance ladder. just a ratio of two wavelengths. Converting redshift into a time requires a cosmological model, how fast the universe was expanding at each stage, which depends on how much matter and dark energy it contains. With the standard model, the conversion is well determined. Redshift 0.7 corresponds to a universe about 7 billion years old. Redshift 1.3 to about 4¾ billion. Redshift 2 to about 3⅓ billion. Redshift 6 to under a billion. The consequence is what makes this entire field possible. Because light travels at a finite speed, looking at a distant galaxy is looking at a past epoch, and the redshift tells you exactly which one. A survey that observes galaxies at many redshifts is not taking a census of the present universe. It is taking a series of photographs of the same universe at different ages. That is why we can measure a history at all. We are not inferring the past from what survived. We are watching it directly at a delay. There is something quietly extraordinary in that arrangement, and it is easy to stop noticing. The information about what the universe was doing 10 billion years ago is not gone. It is in transit. It arrives every clear night on schedule and has been arriving the entire time anyone has bothered to look. The trick that makes the measurement possible is that most stars are invisible for this purpose, and that turns out to be an advantage. Here's the problem. If you point a telescope at a distant galaxy, you collect light from every star in it. Old stars, young stars, everything mixed into a single smear of brightness. You cannot resolve them. A galaxy 10 billion light years away is a smudge a few pixels across. If all those stars contributed equally to what you see, you would have no way to separate the light of stars born last week from the light of stars born 9 billion years ago, and the measurement would be hopeless. But they do not contribute equally, because stars are extraordinarily unequal. A star's luminosity climbs steeply with its mass. Double the mass, and you do not double the light output. You multiply it by something closer to 10. A star of 20 solar masses can outshine the sun by tens of thousands of times, and the same relationship works in reverse on lifetime. The more massive a star is, the faster it consumes itself. The sun will burn hydrogen in its core for about 10 billion years. A star of 20 solar masses will burn through its entire supply in roughly 10 million. It has more fuel, and it spends it 1,000 times faster. Those two facts together give you a stopwatch. Massive stars are hot, and hot objects radiate at short wavelengths. A star with a surface temperature of 30,000 Kelvin puts most of its output into the ultraviolet, far past what your eye can see. The sun, at 5,800 Kelvin, puts most of its output into visible light and barely registers in the far ultraviolet. So if you build an instrument that measures only ultraviolet light at a wavelength near 1,500 angstroms, you have built an instrument that is nearly blind to ordinary old stars and exquisitely sensitive to the very massive ones. And because those massive stars live only about 10 million years, and in some cases far less, every one of them that you detect must have been born recently. There is no other possibility. A star that only lasts 10 million years and is shining now was made within the last 10 million years, which, on a cosmic clock, is the same as saying it was made this instant. That is the whole conceptual foundation. Ultraviolet brightness is not a measure of how many stars a galaxy has. It is a measure of how fast a galaxy is making them right now. The calibration is worked out with stellar population models. If a galaxy forms stars steadily, its ultraviolet output climbs at first and then levels off, because the rate at which new massive stars appear comes into balance with the rate at which existing ones die. For a population of solar composition, the brightness at 1500 angstroms reaches about 75% of its final value after roughly 30 million years, and creeps the rest of the way after that. Once you know where that plateau sits, the conversion is a single multiplication. This much ultraviolet luminosity corresponds to this much new stellar mass per year. You are looking at the fastest burning fraction of a population and inferring the whole. It works for the same reason a doctor can estimate a fever from the flush in someone's face rather than counting individual cells. The bright, short-lived tracer is standing in for something you cannot see directly. That inference contains an assumption, and the assumption is doing more work than it appears to. When you convert ultraviolet light into a star formation rate, you are counting massive stars and then multiplying up to get the total mass in all stars, including the far more numerous small ones that produce almost no ultraviolet at all. To do that multiplication, you need to know the ratio, how many small stars accompany each massive one. That ratio is called the initial mass function, and it describes the distribution of masses a burst of star formation produces. Observationally, the distribution is steep. For every star born with 20 times the sun's mass, hundreds are born with less than the sun's mass. The classic form, used as the reference throughout the major review of this field, is a power law with a slope measured near the middle of the last century, applied across the range from 1/10 of a solar mass up to 100 solar masses. Under that assumption, ultraviolet luminosity converts to star formation rate through a factor of about 1.15 times 10 to the minus 28th in the standard units. Infrared luminosity, integrated from 8 to 1,000 microns, converts through a factor of about 4.5 times 10 to the minus 44th. Those two constants carry the entire field on their backs. And here's the honest part. If the initial mass function is not universal, if galaxies at the peak of cosmic star formation, forming stars furiously in dense metal-poor gas, produced a different mix of masses than a quiet spiral does today, then every rate ever published is off by a factor that varies with cosmic time, and the shape of the curve changes. This is not a fringe concern. It is the single largest systematic uncertainty in the subject, and the people who built the curve say so plainly in their own review. What keeps the assumption credible is that a completely independent check exists. There are two ways to describe the star-making history of the universe. The first is the rate, how much is being made at each moment. The second is the inventory, how much stellar mass exists at each moment. These are related the way a faucet is related to the water in the tub. If you know the flow rate over time and you know how much leaks back out, because dying stars return a fraction of their mass to the gas, you can integrate the flow and predict the level. Then you go measure the level directly by counting up the stellar mass in galaxies at different epochs and see whether the two agree. They agree. Under the assumption of a universal initial mass function, the stellar mass density measured at any epoch matches, reasonably well, the time integral of all the preceding star formation. Integrating the fitted rate forward from the beginning with a return fraction of about a quarter gives a present-day stellar mass density of 5.8 times 10 to the 8th solar masses per cubic megaparsec. The directly measured value from surveys that count galaxies and weigh their stars is 6 times 10 to the 8th, give or take 1. Two completely different measurements made with different telescopes, different techniques, and different sources of error, landing within a few percent of each other. That is the reason to believe the curve. It is also, incidentally, a sobering number in its own right. That stellar mass density corresponds to a stellar baryon fraction of only 9%. Of all the ordinary matter in the universe, all the protons and neutrons, everything that is not dark matter or dark energy, only about 9% has ever been locked into stars. The other 91% is still gas, most of it spread thin between the galaxies, too hot or too diffuse or too isolated ever to collapse. The universe is not a place that turned itself into stars. It is a place that turned about 1/10 of its available material into stars and left the rest lying around. There is a second problem with the ultraviolet method, and for 30 years it made the whole enterprise unreliable. Dust, the same clouds that collapse into stars, are full of solid grains, carbon and silicate particles a fraction of a micron across, condensed out of the winds and explosions of earlier generations. Those grains are very good at absorbing exactly the light we were just relying on. Ultraviolet photons are the most energetic ones in the optical part of the spectrum, and they are absorbed preferentially. A newborn star cluster is typically still wrapped in the remains of the cloud that made it, which means the light we use to detect it is the light most likely to be intercepted before it leaves. So a young galaxy can be building stars at a furious rate and appear in the ultraviolet to be doing very little. The energy is not destroyed, though. It is absorbed by the grains, which warm to a few tens of Kelvin and re-radiate in the far infrared. Nothing is lost, it is only moved. A galaxy that hides its star formation in the ultraviolet betrays it in the infrared, glowing at wavelengths of 100 microns and beyond, where the human eye and ordinary telescopes cannot follow. Which means the ultraviolet census is not a census. It is one page of a two-page ledger. Correcting for this took decades and a series of purpose-built space observatories, because the far infrared is blocked by the atmosphere and requires cold instruments in orbit. The critical work came from surveys that mapped the same patches of sky in the ultraviolet and in the far infrared and simply added the two together. In the deepest of those observations, individual sources directly account for about 75% of the total infrared background at 100 and 160 microns, and stacking analyses recover most of the rest. That is close enough to a complete accounting to be trusted. The scale of the correction is worth stating clearly. Near the peak era of cosmic star formation, the infrared contribution is not a modest addition to the ultraviolet number. It is comparable to it or larger. Galaxies at that epoch were dustier, denser, and more chaotic than galaxies now, and a large fraction of their output was reprocessed into heat before it escaped. Any version of the curve built from ultraviolet light alone underestimates the peak substantially, and therefore understates how far the rate has fallen since. There is a certain irony in this. The dust that hides star formation is itself a product of star formation. Every grain was manufactured by a previous generation of stars and expelled into the gas. So the universe built, out of its own output, the exact material that makes its output hardest to count. The record and the thing obscuring the record have the same author. Put the two pages together and you get the curve. The modern version comes from combining hundreds of published measurements, ultraviolet luminosity functions from deep space telescope imaging, infrared luminosity functions from far infrared observatories, all converted onto a common calibration, all integrated down to a consistent depth so that faint galaxies are counted the same way at every redshift. That last detail matters more than it sounds. Different surveys reach different depths and occur assembled from measurements that each stop at a different faintness would have a shape driven by instrument sensitivity rather than by the universe. What emerges is a single smooth function with three distinct phases. The first phase is a rise. From the earliest epochs we can observe, somewhere around 400 million years after the Big Bang, out to a cosmic age of a couple of billion years, the rate climbs steeply. In the language of redshift, the rate scales roughly as 1 plus redshift to the power of minus 2.9 across the range, from redshift 8 down to redshift 3. Which is a compact way of saying it went up by roughly a factor of 10, while the universe aged from 600 million years to 2 billion. The second phase is the peak. The climb slows, flattens, and turns over somewhere between redshift 2 and redshift 1.5, when the universe was about 3.5 billion years old, roughly a quarter of its present age. The third phase is the decline. From that maximum to the present, the rate falls, following a curve that behaves approximately as 1 plus redshift to the power of 2.7. Below redshift 1, the data can be fit just as well by a simple exponential decay in cosmic time, with an e-folding time scale of 3.9 billion years. That is a clean way to state it. Every 3.9 billion years, the universe's rate of making stars drops by a factor of e, about 2.7. The whole thing is captured by a compact fitting function. The rate equals 0.015 times 1 plus redshift to the 2.7 power, divided by 1 plus the quantity 1 plus redshift over 2.9, raised to the 5.6 power in solar masses per year per cubic megaparsec. 4 numbers. That is the star-making history of the universe, as tightly as anyone has yet been able to write it. You can put that function into a calculator and ask it anything you want. Ask it where the maximum sits, and it says redshift 1.86. Ask it how high the maximum is, and it says 0.133. Solar masses per year per cubic megaparsec. Ask it for the value today at redshift 0, and it says 0.0150. Divide the second number by the third. The universe is currently building stars at about 1/9 the rate it managed at its peak. Take a moment with that ratio because it is the anchor for everything that follows, and it is easy to let it slide past as just another number. 1/9, not a slowdown, not a dip, a reduction to about 11% of what the same volume of space was doing when the universe was 3.5 billion years old. Imagine a manufacturing floor with 9 production lines running. That is the universe near its peak. Now walk back into the same building today, and 8 of the 9 lines are dark. Tools stowed, lights off, and the 9th is still running at its normal pace with a reduced crew. Nothing has broken. Nothing exploded. The building is intact, the remaining line is producing perfectly good work, and the total output is 1/9 of what it was. That is the situation, and it is not a temporary shift. The comparison holds in a specific way that is worth spelling out. This is not a statement about individual galaxies getting worse at making stars, although many of them have. It is a statement about the sum. Some galaxies today are forming stars vigorously. There are starbursts in the local universe converting gas at rates of tens of solar masses per year, but there are far fewer of them, and the typical galaxy contributes far less. And when you add up the entire population inside a moving box, the total is down by that factor of 9. There is one more thing the ratio does not say. It does not say the universe is 1/9 of the way to running out. The decline is not linear, and it is not headed toward a cliff. It is an exponential tail, which means it will keep falling by proportional amounts over enormous stretches of time, always getting smaller, never quite reaching zero on any time scale you would call normal. We will come back to what that tail looks like much later tonight, because the answer is stranger than either it stops or it continues. For now, hold the shape in your head. Up for 3.5 billion years, over the top, down for 10 billion to 1/9. And notice where you are on it. Everything you have ever seen, every constellation, every photograph from every observatory, every human observation of the sky in all of history has been made from a vantage point on the falling limb of that curve, deep into the decline, at a moment when the universe's construction of stars had already been slowing for longer than the Earth has existed. We are not watching the universe make stars. We are watching the end of a very long shift. To understand what was lost, you have to picture the peak. And the peak did not look like the sky you know. Astronomers call that era cosmic noon. It runs roughly from Redshift 3 to Redshift 1.5. A stretch of cosmic time from about 2 billion to about 4.5 billion years after the Big Bang. It is when the majority of the universe's stellar mass was assembled, when supermassive black holes did most of their growing, and when the galaxies we live among acquired the shapes they have now. A galaxy at cosmic noon was a different kind of object. Take a typical massive star-forming galaxy from that era. It contains roughly as much stellar mass as the Milky Way, but it is smaller, often only a few kiloparsecs across, so the same material is packed into a fraction of the volume. Its gas fraction is enormous. Where a modern spiral might hold 10% of its baryonic mass as cold gas, these galaxies commonly held 40 or 50%. They were, by weight, nearly as much fuel as star. That gas was turbulent. Instead of settling into a thin, orderly disk with graceful spiral arms, it fragmented into a handful of giant clumps, each one hundreds of parsecs across and containing 1 billion solar masses, each one collapsing and forming stars at a rate that would look violent by local standards. Deep imaging of these objects shows them as chains and knots of blue light rather than smooth disks. They look unfinished because they were. The star formation rates involved are the part that reframes everything. A galaxy of that mass at cosmic noon typically forms stars at 50 to 100 solar masses per year, sustained for hundreds of millions of years. The Milky Way today forms stars at between 1 and 2 solar masses per year. Put those side by side. The same amount of stellar mass in a smaller volume, building itself 30 to 50 times faster. And there were more of them. The comoving number density of vigorously star-forming galaxies was far higher than it is now, and they were physically closer together because the universe was smaller. At Redshift 2, every distance between galaxies was a third of what it is today. Encounters, tidal disturbances, and outright mergers were routine rather than exceptional, and each of those events compresses gas and triggers more star formation. If you could stand somewhere in that universe and look up, you would not see anything you would recognize. There would be no ordered spiral pinwheels overhead. There would be irregular, knotted, luminous shapes, some of them blue enough to look almost violet through dust, packed closer together, many of them visibly interacting. The whole sky would be brighter and hotter in color. That was the maximum. Everything since has been a descent from it. Now put actual numbers on the descent, because the numbers are more specific than the picture. At the crest of the curve, the universe was converting 0.133 solar masses of gas into stars every year, inside every cubic megaparsec of comoving space. Today, the same volume produces 0.0150. Those two figures come from the same fitted function, evaluated at two different times, so the comparison is internally consistent. The absolute values carry the systematic uncertainty of the calibration. Change your assumption about the initial mass function, and both numbers move together. But the ratio between them is far more robust than either one alone, because the systematic error largely divides out. The universe made stars about 9 times faster then than now, and that statement survives most of the things that could be wrong with the measurement. Convert those rates into something you can hold. A cubic megaparsec, filled with roughly 100 galaxies of various sizes, produced about 1 solar mass of new stars every 7.5 years at the peak. Today, the same box takes about 67 years to produce 1 solar mass. Over 1 million years, a period so short in stellar terms that the constellations barely shift. The peak era box built 130,000 solar masses of new stars. The modern box builds 15,000. Another way to hold it, at the peak rate, the universe assembled the equivalent of an entire Milky Way's worth of stellar mass, about 60 billion solar masses, inside every comoving volume of 450,000 cubic megaparsecs, every million years. The bookkeeping is dizzying at any scale. The ratio stays the same. There is a subtlety in the peak value that deserves an honest mention. The fitting function places the maximum at redshift 1.86, which corresponds to about 3.5 billion years after the Big Bang. But the people who wrote that function say directly that the peak cannot be pinned down within a redshift interval of 1. The data around cosmic noon are dense, but the corrections are largest precisely there. The dust is thickest, the infrared luminosity function is least certain at its faint end, and the extinction corrections applied to ultraviolet measurements carry their own scatter. Everyone agrees there is a peak. Everyone agrees it is near Redshift 2, and nobody can tell you whether it was at 1.6 or 2.2. That uncertainty does not touch the conclusion. Whether the maximum was at redshift 1.6 or 2.2, it was more than 9 billion years ago, and the rate today is roughly a ninth of it. The rate is only half the story, though, and the more startling half is the inventory. A rate tells you what is happening now. An inventory tells you what has accumulated. And because stars, once made, mostly persist, a point we will return to at length, because it is the hinge of this entire episode. The inventory is a running total of everything the universe has ever built. Integrate the curve. Start at the beginning. Add up all the star formation at every epoch. Subtract the fraction that dying stars return to the gas, and ask, at what point in cosmic history had the universe assembled half of the stellar mass that exists today? The answer is redshift 1.3. In cosmic time, that is roughly 4.75 billion years after the Big Bang. The universe is now about 13.8 billion years old. So half of all the stellar material in existence tonight was already in place before the universe had lived out its first 5 billion years, before it had completed the first third of its life to date. Half of every star that exists tonight was already burning before the universe was 5 billion years old. Notice what that means for the Earth. Our planet formed about 4.5 billion years ago, when the universe was roughly 9 billion years old. By the time there was a sun and a disk of debris around it, and eventually a rocky world with an ocean, the universe had already made well over half of everything it would ever make. The Earth is not an early feature of cosmic history. It is a late one, assembled in the long afternoon, out of material that had already been through several generations of stellar processing. You can hear that as diminishing. It is not, particularly. Being late has advantages. The heavy elements that make a rocky planet possible did not exist in useful quantities in the early universe. They had to be manufactured first. A planet like this one could not have formed at cosmic noon because the raw material was not ready. We are late because the chemistry had to be built first, and building it took most of the star formation the universe would ever do. Still, the ledger is the ledger. More than half of the stellar mass in the universe predates the sun. Most of the stars whose light reaches your window tonight were already in existence before the solar system had a single planet in it. The split gets sharper when you look at the quarters rather than the halves. About 25% of today's stellar mass formed before the peak of the star formation rate, before redshift 2, in the first 3.5 billion years. Another 25% formed after redshift 0.7, which is to say in the last 7 billion years or so, the entire second half of the cosmic history. Do the subtraction in the middle half, 50% of everything, was assembled in the interval between redshift 2 and redshift 0.7. That is a window of about 3.75 billion years out of a 13.8 billion year history. Roughly 27% of the universe's lifetime produced 50% of its stars. That interval is the peak and the first part of the decline. It is the era when the rate was within a factor of 2 of the maximum, high enough to build at speed, long enough to build a great deal. If you wanted to name a single epoch as the one in which the universe furnished itself, that is the one. The symmetry of the two quarters is worth pausing on because it defeats the intuition most people have. The obvious guess, if you know that star formation peaked long ago, is that almost everything was made early and the recent universe has contributed a rounding error. But the last 7 billion years produced a full quarter of all stellar mass. That is not negligible. It is the same fraction as the entire pre-peak era, including all the earliest galaxies, the first massive stars, and the whole buildup to cosmic noon. The decline is slow. That is the point. An exponential with an e-folding time of 3.9 billion years does not fall off a cliff. It descends gently enough that even the tail contains a great deal of construction. A quarter of everything made on the way down. There is a version of this story that gets told as an obituary. The universe's creative period is over. Everything since is aftermath. The numbers do not support that framing. What they support is something more measured. The universe had a peak era. It built half of everything in a window centered on that era. And it has spent the time since building the last quarter more and more slowly. That is a decline. It is not a collapse, and it is not finished. At the other end of the curve, the numbers cut the other way, and they cut hard. Less than 1% of today's stars formed during the epoch of reionization. Reionization is the transition. Somewhere between roughly 400 million and 1 billion years after the Big Bang, when the ultraviolet output of the first galaxies stripped electrons off the neutral hydrogen filling the universe and turned it transparent. It is one of the most studied problems in cosmology and one of the most difficult. Enormous observational effort is aimed at that era, and rightly. It is where galaxies begin, where the first heavy elements appear, and where the universe transitions from dark to lit. But as a contribution to the stellar inventory, it is a rounding error, less than 1%. The same review that gives us the curve puts a related number on it. Stars formed in galaxies more than 11.5 billion years ago are predicted to contribute only 8% of the total stellar mass today. Almost everything you are looking at when you look at the night sky was made in the more recent 2/3 of cosmic history. And the corollary, galaxies formed the bulk of their stellar mass, at least 75% of it, after Redshift 2. Those two facts, held together, are the correct summary of the early universe's role. It was decisive, and it was small. Decisive because it produced the first heavy elements, the first dust, the first black holes, and the conditions under which everything later became possible. Small because in raw mass, the first billion years contributed less than 1 part in 100 of what exists now. The metal budget makes the same point from another direction. By Redshift 6, 1 billion years in, the mean metallicity of the universe had climbed to about 1,000th of solar. 1 part in 1,000 of the enrichment we see around us today, after 1 billion years of work. The universe at that point had been doing chemistry for a long time by human standards, and had produced almost nothing by its own eventual standards. And there's a tension buried in those early numbers that has not gone away. The same accounting finds that this early star formation produced fewer than 10 hydrogen ionizing photons per baryon, a tight budget for reionizing the entire universe. It is not comfortably enough. It works only if a high fraction of those photons escape their galaxies, which is difficult to arrange and difficult to measure. The people who did the accounting call it a rather tight budget, which in the language of a review article is a way of saying that something here is not yet fully understood. Hold that thought. It becomes important later when we talk about what the newest telescopes have found at the beginning of the curve. A curve assembled from hundreds of heterogeneous measurements deserves at least one independent test, and the field has one. In the early 2010s, a team led by David Sobral used 3 telescopes: the United Kingdom Infrared Telescope, Subaru, and the Very Large Telescope, to run a set of narrow-band surveys aimed at a single spectral line. Not the ultraviolet continuum, the hydrogen alpha line at 656 nanometers in the rest frame, produced when ionized hydrogen recombines in the gas surrounding hot young stars. Hydrogen alpha is a good tracer for a reason worth understanding. It is not the light of the young stars themselves. It is the light of the gas they are ionizing, which means it responds almost instantly to the presence of massive stars and stops almost instantly when they die. It tracks star formation on a timescale of a few million years rather than 100 million. And it sits in the optical, where dust extinction is real but far less severe than in the ultraviolet. The design of the survey is what makes it valuable. Rather than compiling measurements from many different programs with different depths and different methods, the team observed 4 specific redshifts: 0.40, 0.84, 1.47, and 2.23, with the same technique over the same 2 square degrees of sky in 2 independent fields. Look-back times of 4.2, 7, 9.2, and 10.6 billion years. One method, 4 epochs, uniform selection. That is the cleanest possible way to measure a change over time, because the systematic errors are identical at every point and largely cancel when you compare. They found 1,742 emitters at the nearest epoch, 637 at the next, 515 at the next, and 807 at the most distant. The faint end slope of the luminosity function turned out not to evolve at all over that entire span, staying at about minus 1.6. What changed was the characteristic luminosity. Bright star-forming galaxies at redshift 2.2 were simply much brighter than their counterparts today, by a factor that grows steadily with redshift. Their conclusion, stated in their own summary, is that star formation since redshift 2.2 is responsible for about 95% of the stellar mass density observed locally today, with half of it assembled between redshift 1.2 and 2.2 and the rest since redshift 1.2. Line that up against the other result, and you have 2 teams, 2 methods, 1 broad agreement. The bulk of the stellar mass is old. Most of it comes from the peak era and the early decline, and the recent universe contributes a real but shrinking share. And here's the thing nobody likes to say plainly about results like this. The 2 analyses do not actually agree on how steep the decline has been. The compiled ultraviolet plus infrared curve gives a factor of about 9 between the peak and now. The hydrogen alpha survey, extrapolated, implies something considerably steeper. The figure that circulated widely was that the present rate is around 3% of the peak, a factor of 30. Both are careful pieces of work. They are measuring the same universe with different tracers, and they get answers that differ by a factor of 3. That disagreement is not a scandal. It is what the subject looks like from the inside, and it is worth understanding why. Every tracer of star formation is an indirect measurement wearing a conversion factor. Ultraviolet continuum light needs a dust correction and an assumption about the initial mass function. Infrared light needs a model of how dust grains absorb and re-emit, and a decision about how much of the infrared glow comes from young stars versus older ones warming the same dust. Hydrogen alpha needs its own extinction correction and a treatment of how much of the line flux is lost to the surrounding gas. Radio continuum needs a calibration against supernova rates. Each method has a different blind spot. At low redshift, where galaxies are nearby and can be studied in detail, the methods mostly agree. As you push to higher redshift, the corrections grow and the disagreements widen. The dustiest galaxies drop out of ultraviolet surveys entirely. The faintest galaxies drop out of infrared surveys because far infrared observatories have poor angular resolution and confusion limits that bite quickly. Each survey is complete for a different subset of the population, and stitching them into one curve requires judgments that reasonable people make differently. Then there is the question of how deep to integrate. A luminosity function does not terminate. It continues to fainter and fainter galaxies. The total star formation rate you calculate depends on where you stop counting. One standard choice is to integrate down to 3% of the characteristic luminosity, which captures the great majority of the light, but not all of it. Choose a different limit and your total moves. Compare two studies that chose differently, and you have manufactured a disagreement out of bookkeeping. There is also the deeper problem of comparing rates measured on different clocks. Ultraviolet continuum averages star formation over about 100 million years. Hydrogen alpha averages it over a few million. In a galaxy whose star formation is bursty, flaring and quieting on timescales of tens of millions of years, which appears to be common in low-mass galaxies, those two tracers can give genuinely different answers about the same object, and neither one is wrong. They are answering different questions. So when two careful analyses land a factor of 3, apart on the steepness of the decline, the correct response is not to pick the more dramatic number. It is to notice what they agree on. They agree there was a peak. They agree it was near redshift 2. They agree the rate has fallen a long way since. They agree that the majority of stellar mass was assembled before the solar system existed. We will use the factor of 9 tonight because it comes from the most comprehensive compilation, and it is the more conservative of the two. If the steeper result is closer to the truth, every conclusion in this episode becomes stronger, not weaker. Which brings us to a specific star, at a specific point on that declining curve. The Sun formed about 4.57 billion years ago. That places its birth at a cosmic age of roughly 9 billion years, at a redshift of about 0.4. Evaluate the curve there. At redshift 0.4, the universe was forming stars at about 0.037 solar masses per year per cubic megaparsec, approximately 27% of the peak rate. So the Sun was born into an era already well into decline. Not the tail, but not the good years either. The universe had already made more than half of all the stellar mass it now contains. The peak was 5.5 billion years in the past. The rate had already dropped by a factor of nearly 4 from its maximum and was continuing to fall. There's a particular texture to that fact when you take it personally. The star you orbit is not one of the universe's early works, and it is not one of its last. It formed in the middle of the long descent, out of gas that had already been enriched by generations of stars that lived and died before the solar system had a location. Every iron atom in your blood, every calcium atom in your bones, was manufactured in a star that had already finished its life before the sun ignited. You are made of secondhand material, and the recycling had been going on for 9 billion years by the time it reached you. This is also the reason the solar system has planets like this one. The gas that formed the sun carried about 1.4% of its mass in elements heavier than helium, a metallic city high enough to build a rocky world with an iron core and a supply of water. A star forming at cosmic noon, out of gas that had been through far fewer cycles, would have had a much thinner supply of solids to work with. The universe had to spend most of its star formation to reach the point where a planet like yours became a routine outcome. Consider what that means about timing. If you imagine a version of this planet forming much earlier, in the era when the universe was building stars 9 times faster, the raw material for it would not have existed. There is a real sense in which a world with an ocean and a crust and an atmosphere had to wait for the factory to be most of the way through its run. The lateness is not an accident of your particular star. It is close to a requirement. So why did the rate fall? The answer has several parts, and the first one is the simplest. The universe ran low on the specific kind of gas that makes stars. Not gas in general. There is an enormous amount of ordinary matter still out there. Remember, only about 9% of the baryons in the universe have ever been in a star. The problem is that most of that material is in the wrong state. Stars form only out of cold, dense, molecular gas, hydrogen in molecular form, at temperatures of 10 to 20 Kelvin, at densities high enough that a cloud's own gravity overwhelms its internal pressure. That is a demanding set of conditions, and only a small fraction of the universe's hydrogen is ever in that state at any given moment. Think of it as a hardware store with full shelves and no delivery truck. The building is stocked. The intergalactic medium holds far more hydrogen than every galaxy combined, but it is spread across millions of light years at densities of 1 atom per cubic meter, heated to millions of Kelvin by the shocks of structure formation. It cannot form a star any more than fog can form a brick. The material is present and unusable. What makes a galaxy productive is not how much gas exists nearby, but how fast cold gas is arriving. And in the early universe, cold gas arrived constantly. The mechanism has a name: cold mode accretion. In a young universe, matter is arranged along a web of filaments, and galaxies sit at the intersections. Gas flows down those filaments and into the growing galaxies in narrow, dense streams. Crucially, in a low-mass halo, that gas never gets hot. It flows in at a temperature low enough to be immediately available for star formation, delivered directly to the disk without passing through an intermediate stage. The supply line runs straight from the cosmic web to the assembly floor. That was the arrangement for the first few billion years, and it is the reason cosmic noon was possible. Galaxies were not making stars quickly because they were better at it. They were making stars quickly because they were being fed continuously from outside with exactly the material they needed. The decline in star formation is, more than anything else, the story of that feeding stopping. It stopped for a reason that is elegant and, once you see it, almost inevitable. As a dark matter halo grows more massive, gas falling into it moves faster because the gravitational potential is deeper. Fast-moving gas that runs into other gas produces a shock, and a shock converts ordered motion into heat. Above a threshold halo mass, somewhere near 100 trillion times the mass of the Sun, though the exact value depends on details, infalling gas no longer reaches the center cold. It shock heats on the way in and settles into a hot, roughly spherical atmosphere at the virial temperature of the halo, which for a large galaxy is 1,000,000 Kelvin or more. A galaxy that has built one of these hot halos has effectively insulated itself from its own fuel supply. The gas is there, surrounding it in enormous quantity. It simply cannot get in, because to get in, it would first have to cool, and cooling from 1,000,000 Kelvin at low density is slow. The cooling time can exceed the age of the universe, so the galaxy switches from being fed to being self-sufficient, and self-sufficiency is fatal to a star-forming galaxy because it now has only what is already inside it. This threshold behavior explains a great deal of what the curve does. It explains why the most massive galaxies stopped forming stars first and why they did so earliest. They crossed the mass threshold soonest. It explains why star formation persists longest in low-mass systems, which never build a stable hot atmosphere and can keep drawing cold gas from their surroundings. And it explains why the transition across the whole population looks gradual. Halos cross the threshold at different times depending on their mass and environment, so the shutdown is spread over billions of years rather than happening all at once. It also explains something you can see with your own eyes in the difference between the two great classes of galaxy. Spirals are gas-rich, blue in color because they contain young massive stars and still forming stars at a modest rate. Ellipticals are gas-poor, red because their stellar population is uniformly old and forming almost nothing. That is not a difference of shape. It is a difference of plumbing. An elliptical is a galaxy whose supply line closed a long time ago and which has been coasting on inventory ever since. The universe today is progressively converting the first category into the second, one galaxy at a time, and there is no known mechanism that runs the process backward. You can watch the fuel disappear directly, and this is one of the more satisfying confirmations in modern astronomy because it measures the cause rather than the effect. Molecular hydrogen is nearly impossible to detect in cold gas. The molecule is symmetric, has no permanent dipole moment, and its lowest transitions require temperatures far higher than the 10 to 20 Kelvin found in star-forming clouds. So the standard technique uses carbon monoxide as a proxy. Carbon monoxide is far less abundant than hydrogen, but it radiates readily at millimeter wavelengths even in cold gas, and its brightness can be converted into a total molecular gas mass through a calibration factor. With enough sensitivity, you can survey a patch of sky for carbon monoxide emission at every redshift simultaneously by scanning across frequency. The same physical line shows up at different observed frequencies depending on how far away the galaxy is. Do that deep enough, and you get a census of molecular gas across cosmic time. That is what the ALMA array in the Atacama Desert was built to do, and a series of deep spectroscopic surveys of small patches of sky have now produced it. The result tracks the star formation curve. The cosmic density of molecular gas rises from the early universe to a peak around redshift 1.5, climbing by roughly a factor of 7 from its present value, and then falls back down again by a factor of about 6 from the peak to today. That is the underlying cause, measured independently of the star formation it produces. Galaxies today are not less efficient at converting gas into stars. They have less gas to convert. The efficiency, as far as anyone can measure it, has stayed roughly constant. Give a galaxy a certain amount of cold molecular gas, and it will turn a similar fraction of it into stars per unit time, now as it would have 9 billion years ago. What changed is the amount on hand. That is the shape of the whole argument in one sentence. The universe is currently building stars at about 1/9 the rate it managed at its peak. And the reason is not that it forgot how, it is that the cold gas ran down. There's an asymmetry in those two numbers worth noticing. Molecular gas is down by 6, star formation by 9. The gap is real and probably reflects a modest decline in efficiency as well as supply, related to how gas is distributed inside galaxies now compared to then. Modern spirals hold their molecular gas in extended, low-density disks. Cosmic noon galaxies packed it into dense clumps where star formation runs faster. Same material, different arrangement, different output. There's a number that follows from all of this, and it is the one that decides the future. If you take a star-forming galaxy today and measure how much molecular gas it contains, and then divide that by how fast it is converting gas into stars, you get a depletion time. How long the galaxy could continue at its current rate before the tank is empty. For a typical spiral, the answer is between 1 and 2 billion years. That is short. Not short in human terms, but very short compared with the age of the universe, and startlingly short compared with the time such a galaxy has already been forming stars. The Milky Way has been making stars for well over 10 billion years. It has enough molecular gas left for 1 or 2 more billion at the current rate. Which raises an obvious question. How has it kept going this long? The answer is that a galaxy is not a closed tank. It has been refilled continuously from 3 sources. Some cold gas still falls in from outside, even into galaxies with hot halos, along the residual filaments and in the form of cool clouds that survive the passage. Some gas is returned by dying stars, which give back a substantial fraction of their mass through winds and explosions. The return fraction is roughly a quarter of everything ever formed, and that material is enriched and can form new stars. And some gas is recycled through galactic fountains, where material blown out of the disk by supernovae falls back down after cooling, sometimes tens of millions of years later. Between them, those 3 processes have kept most spirals roughly in balance for billions of years, at a rate set not by how much gas is in the disk, but by how fast new gas arrives. That is why galaxies with short depletion times can nevertheless form stars for far longer than that time. They are not draining a reservoir, they are running a pipeline, which tells you exactly what the decline is. The pipeline is being throttled. External accretion falls off as halos grow hot and as the expansion of the universe dilutes the surrounding medium. Stellar return falls off as the population ages and fewer massive stars die per unit time. Fountain recycling continues, but it is a loop, not a source. It cannot add material that was not already there. So the depletion time is not a countdown to the end of star formation. It is a measure of how tightly a galaxy is coupled to its supply. When the supply weakens, the output follows within a couple of billion years. And that lag, 1 or 2 billion years between a change in supply and a change in output, is one reason the cosmic curve declines as smoothly as it does rather than in steps. There is a pattern in how the decline shows up galaxy by galaxy, and it is tidier than anyone expected. If you take a large sample of star-forming galaxies at a single epoch and plot each one's star formation rate against its stellar mass, the points do not scatter randomly. They fall along a narrow band. More massive galaxies form more stars, following a relation that is close to proportional, with a scatter of only about a factor of 2 around it. The relation is usually called the star-forming main sequence, borrowing the name from the diagram used for individual stars, though the two have nothing physically in common. The existence of that band is itself informative. It means star formation in most galaxies is not episodic and chaotic. It is a smooth, regulated process set by a galaxy's mass and its gas supply, not by whatever bursts it happens to be having. Galaxies well above the band are the rare starbursts, usually triggered by interactions, and they contribute only a small fraction of the cosmic total. Most star formation happens in ordinary galaxies doing ordinary things. Now measure that band at different redshifts, and the decline appears in its simplest possible form. The slope of the relation stays roughly the same. The scatter stays roughly the same. What changes is the normalization. The entire band slides downward with cosmic time. A galaxy with the Milky Way's stellar mass at redshift 2 sits on a band an order of magnitude higher than a galaxy of the same mass today. Same mass, same kind of object, forming stars 20 or 30 times faster. That is a remarkably specific statement about what happened. The universe did not decline by converting star-forming galaxies into dead ones, one at a time, with the survivors carrying on unchanged. Both things happened at once. Galaxies were progressively removed from the star-forming population as they quenched, and simultaneously, the ones that remained were forming stars more slowly than their predecessors of the same mass. Two effects working together. Fewer participants and each participant working at a reduced pace. When you decompose the cosmic decline into those two contributions, the fading of the main sequence turns out to dominate. Most of the drop in the cosmic star formation rate is not because galaxies shut down. It is because the ones still running are running slower, for the reason we have already established. They have less cold gas per unit of stellar mass than their ancestors did. The universe is currently building stars at about 1/9 the rate it managed at its peak, And the largest single contribution to that ratio is the simple fact that an ordinary spiral galaxy today is a quieter object than an ordinary spiral galaxy was 9 billion years ago. The gas supply is the main story, but there is a second mechanism working alongside it, and this one is internal. Star formation destroys the conditions that permit star formation. A massive star does not simply sit there radiating. It floods its surroundings with ultraviolet photons, energetic enough to ionize hydrogen, heating the gas around it from 10 Kelvin to 10,000 and raising the pressure by a factor of 1,000. It drives the wind off its own surface at thousands of kilometers per second, and after a few million years, it explodes, injecting roughly 10 to the 51st ergs of kinetic energy into the cloud that made it. The cloud does not survive this. A giant molecular cloud that begins forming stars typically converts only a few % of its mass into stars before the first generation of massive stars disperses the rest. The cloud is dismantled by its own products on a timescale of a few million to a few tens of millions of years. Zoom out and this becomes a regulator for the whole galaxy. If gas piles up in the disk, star formation rises, and the resulting supernovae inject energy that heats the gas, stirs it into turbulence, and in low-mass galaxies drives it out of the disk entirely in a wind. That reduces the amount of cold gas, which reduces star formation, which reduces the energy input, which lets the gas cool and settle again. It is a thermostat, and it is why galaxies do not simply convert all their gas into stars in a single free-fall time, which, if nothing opposed it, would take only tens of millions of years. The efficiency of that thermostat depends on the depth of the gravitational well. A dwarf galaxy has a shallow well. A single generation of supernovae can eject a large fraction of its gas into intergalactic space, where it will not return for a very long time, if ever. A massive galaxy holds on to more of it. That is one of the reasons small galaxies have such irregular, bursty star formation histories, while large spirals are steady. None of this causes the cosmic decline by itself. Feedback was operating just as strongly at cosmic noon, and star formation was 9 times higher. What feedback does is set the conversion efficiency, the fraction of available gas that becomes stars per unit time. It is the reason that only about 9% of the universe's ordinary matter has ever been in a star, when a universe without feedback would have converted a far larger share. Feedback did not end the boom. It capped the boom while it lasted, and it continues to cap what remains. There is a third actor, and it is the one that operates at the top end of the mass scale. Nearly every massive galaxy has a supermassive black hole at its center, with a mass typically about 1,000th of the mass of the galaxy's central bulge. When gas falls onto one of these objects, the energy released is extraordinary, a few % of the rest mass of the infalling material, converted into radiation and outflow. For comparison, nuclear fusion releases less than 1%. Accretion onto a black hole is the most efficient large-scale energy conversion process the universe has. That energy has to go somewhere, and where it goes is into the surrounding galaxy. The most striking evidence that this matters is a coincidence in timing. Trace the history of black hole growth, measured from the luminosity of quasars and active galactic nuclei across cosmic time, converted into an accretion rate, and you get a curve that rises and falls in almost the same pattern as the star formation curve. Both climb through the early universe. Both peak within a couple of billion years of each other. Both decline steeply afterward. The two are not identical. Black hole accretion peaks at somewhat lower redshift than star formation, and it declines more rapidly from redshift 1 to the present. But the parallel is close enough that it is taken as strong evidence for coevolution. Black holes and their host galaxies grew together, fed by the same gas supply, and shut down together when that supply was cut off. The causal arrow probably runs both ways. Gas that reaches the center of a galaxy can form stars or feed the black hole, so both processes rise and fall with the same fuel. But the black hole also acts back on the galaxy. In the most luminous phase, radiation pressure and winds from the accretion disk can drive gas out of the galaxy at thousands of kilometers per second. In a quieter mode, relativistic jets from the black hole deposit energy into the surrounding hot halo, keeping it hot and preventing it from cooling and falling in. That second mode may be the more important one for the cosmic decline. In the largest galaxies and in the centers of galaxy clusters, the hot atmosphere should cool and rain down at rates of hundreds of solar masses per year. Observations show that it does not. The cooling is suppressed by roughly an order of magnitude, and the suppression correlates with jet activity from the central black hole. Something is reheating the gas as fast as it cools. So the picture is a galaxy with 3 breaks on it. Its external supply cut off by shock heating. Its internal gas dispersed by the stars it makes. And its remaining hot reservoir kept from cooling by a black hole that eats a tiny fraction of it and puts out enough energy to keep the rest from settling. Now step back from individual galaxies to the arrangement of them, because the geometry of the universe itself has changed in a way that matters. At redshift 2, every distance between 2 galaxies was 1/3 of what it is today. The universe was smaller by that factor in every direction, which means the same galaxies sat in a physical volume 27 times smaller than the one they occupy now. Picture a photograph of a crowd, taken from above, at the moment the crowd began to disperse. In the first frame, people are shoulder to shoulder. Conversations happen constantly because you cannot avoid your neighbors. In a later frame, the same people occupy a space 3 times wider in each direction, and the encounters that were unavoidable have become rare. Nobody left. The room grew. That thinning has a direct effect on star formation, because galaxy interactions are one of the most reliable ways to trigger a burst of it. When 2 gas-rich galaxies pass close to one another, tidal forces remove angular momentum from the gas, and gas that loses angular momentum falls toward the center, where it becomes dense enough to collapse. A major merger between 2 spirals can produce a starburst converting hundreds of solar masses per year, briefly outshining anything the galaxies did separately. At cosmic noon, those events were common. Deep imaging surveys of that era show a high fraction of galaxies in disturbed or interacting configurations. Today in the field, they're unusual. The Milky Way's last major merger was around 10 billion years ago. Its current interactions are with small satellites that barely disturb the disk. The dilution also weakens accretion. the density of gas in the cosmic web drops as the universe expands, so the streams that once fed galaxies carry less material per unit time. Structure continues to grow. Filaments and clusters become more pronounced, but the average density of everything falls, and accretion rates onto individual halos decline accordingly. There is something almost gentle about this cause compared with the others. No violence, no shutdown, no feedback loop, just distance. The universe made stars quickly in part because it was crowded, and it is not crowded anymore. And then there is the change that makes all of this permanent. For most of cosmic history, the expansion of the universe was slowing. Gravity from all the matter in it acted as a brake, and the expansion rate decreased with time. Under those conditions, structure keeps growing. Regions slightly denser than average pull themselves together, halos merge into larger halos, and the cosmic web continues to sharpen indefinitely. That changed about 5 billion years ago when the universe transitioned from matter-dominated to dark energy-dominated. As matter thinned out with expansion and dark energy did not, the balance tipped, and the expansion began to accelerate. Accelerating expansion sets a hard limit on structure formation. Regions that are already gravitationally bound stay bound. The local group is not going to come apart, but regions that have not yet collapsed will now never collapse because space between them is expanding faster than gravity can pull them together. The growth of structure freezes at the scale it has reached. For star formation, that is decisive. Every galaxy now has, in effect, a final allocation. Whatever gas is inside its bound structure is what it will ever have. There will be no more large-scale accretion from beyond, because the material beyond is receding and will continue to recede at an accelerating pace. Over the next 100 billion years or so, galaxies outside the local group will pass beyond our cosmological horizon entirely. This is the difference between a slowdown and an ending. A slowdown could reverse. A universe that keeps assembling larger structures could produce new mergers, new gas flows, new bursts of construction indefinitely. The accelerating universe cannot. The supply is now fixed at whatever each bound structure holds, and the only way to make new stars is to recycle what is already inside. Set that beside the number we keep coming back to. The universe is currently building stars at about 1/9 the rate it managed at its peak, and the mechanism that would be required to restore the earlier rate, large-scale delivery of fresh cold gas from outside, has been switched off permanently by the geometry of space itself. The decline is not a phase. It is the shape of everything that comes next. It is worth bringing this home to the one galaxy we can examine in detail, because our own history is a compressed version of the cosmic one. The Milky Way forms stars at about 1.65 solar masses per year, with an uncertainty of roughly 0.19, the result of a careful statistical combination of many independent measurements made with different techniques. Some recent infrared work argues for a higher figure, so the honest statement is that our galaxy converts somewhere between 1 and 2 solar masses of gas into stars annually, and that the number is not perfectly settled. Either way, it is a modest rate. 1 or 2 solar masses a year in a galaxy that contains roughly 60 billion solar masses of stars. Our galaxy did not always do this. The evidence for its earlier vigor is written into its structure. The Milky Way has a thick disk, a population of older, metal-poor stars distributed in a layer several times taller than the thin disk we live in. And that thick disk formed early in a period of intense star formation more than 10 billion years ago, probably driven by a major merger with a substantial galaxy whose debris is still identifiable in the motions of stars around us. During that era, the Milky Way was forming stars at rates that may have exceeded 10 solar masses per year, possibly much more. It was, in other words, a cosmic noon galaxy, doing what cosmic noon galaxies did. Then it quieted. The rate dropped over billions of years to its current value, following the same trajectory as the universe as a whole, and for the same reasons. Hot halo, diminishing accretion, gas locked into stars, and remnants that will never return it. There is a detail here that puts the scale in perspective. At its present rate, the Milky Way would need about 36 billion years to produce the stellar mass it already has. It does not have 36 billion years worth of gas, and it will not sustain even this rate for that long. The galaxy you live in has already done the overwhelming majority of its work. Look up at the band of the Milky Way on a dark night, and you are looking at a structure that is essentially complete. Not dead. There are active nurseries in it right now, some of them visible to your unaided eye as faint patches, but finished in the sense that matters. The great construction of this galaxy happened before there was an Earth to watch it from. 1 or 2 solar masses a year is an abstraction until you find out where it is happening. The nearest place is about 1,300 light-years away, in the constellation Orion, and on a clear winter night in the northern hemisphere, you can see it without any instrument at all. Below the 3 stars of Orion's belt hangs a line of fainter points forming the sword, and the middle one is not a star. It is a cloud of glowing gas about 24 light-years across, lit from inside by 4 massive young stars. The Orion Nebula is a blister on the near side of a much larger structure. Behind it lies a molecular cloud complex containing something like 200,000 solar masses of cold gas, most of it invisible at optical wavelengths, detectable only by its carbon monoxide emission, and by the way it blocks the light of stars behind it. Within that complex, several thousand young stars have formed in the last few million years, and more are forming now. That is what the modern rate looks like up close. Not a galaxy-wide event. A handful of active regions scattered around the disk, each converting a few hundred or a few thousand solar masses of gas into stars over a few million years, while the vast majority of the galaxy does nothing at all. Similar regions exist elsewhere. There is one in Taurus, closer than Orion at about 450 light-years, but forming only low-mass stars, so it glows far more faintly. There is one in Ophiuchus and another in Perseus. None of them, individually, would register at cosmic distances. There are perhaps a few dozen comparable complexes in the Milky Way, plus a large number of smaller ones. Add up their output and you get your 1 to 2 solar masses a year. It is a distributed, patchy, intermittent process, nothing like the smooth conversion the cosmic average implies. The stars in Orion's sword are perhaps 1 million years old. The 4 bright ones at the center, The trapezium are massive enough that they will exhaust themselves and explode within a few million more. And when they do, they will disperse most of the remaining cloud and end star formation in that region permanently. What you are looking at on a winter night is a construction site in its final phase, already scheduled for demolition. The next time you are outside on a cold, clear evening and you find Orion, you are seeing one of the very few places in this galaxy where the process that built everything is still visibly running. There are not many left. There will be fewer. Where does the gas that is still forming stars actually live, and what makes it collapse? Almost all of it is in giant molecular clouds, cold, dense, irregular structures ranging from a few thousand to a few million solar masses, spanning tens to hundreds of light years. They are the coldest places in the galaxy, at 10 to 20 Kelvin, cold enough that hydrogen exists as molecules rather than free atoms, and that carbon monoxide, ammonia, water, and dozens of more complex molecules survive on the surfaces of dust grains. These clouds are not uniform. High-resolution mapping shows them shot through with filaments, long, narrow structures a fraction of a light year across and many light years long, laced through the cloud like veins. Star formation happens almost exclusively in those filaments, and preferentially at the points where several of them intersect. That geometry appears to be produced by turbulence. Supersonic motions within the cloud sweep material into sheets. Sheets fragment into filaments, and filaments fragment into cores. A core is the final stage before a star. It is a knot of gas, typically a tenth of a light year across, containing between a fraction of a solar mass and a few solar masses, dense enough that its own gravity has finally beaten everything opposing it: thermal pressure, turbulence, and magnetic fields. Once that balance tips, collapse takes something like 100,000 years, and at the end of it, there is a protostar surrounded by a disk of leftover material out of which planets may form. What is striking is how inefficient the whole arrangement is. A giant molecular cloud with a million solar masses of gas will produce perhaps 10 to 50,000 solar masses of stars over its lifetime. A few percent. The rest is dispersed, heated, blown out, returned to the diffuse interstellar medium to eventually recondense somewhere else, or driven out of the disk entirely. That inefficiency is not incidental. It is why the universe still has gas at all after 13.8 billion years. If star formation converted clouds efficiently, the available material would have been consumed long ago in the first billion years, and the universe would now be a place of nothing but old stars and remnants. The waste is what preserved the process. There's an odd generosity to that. The mechanism that makes stars is bad at its job in exactly the way that lets it keep going. Now we have to be careful about a word, because the title of tonight's episode contains an ambiguity that is worth taking apart. Most of its stars. Most by what measure? Everything discussed so far has been stated in units of mass. Solar masses per year, stellar mass density, half the stellar mass formed before Redshift 1.3. Mass is what the observations actually constrain, because luminosity converts to mass and the integral of a rate is a mass. but most of its stars sounds like a count, a number of objects, not a quantity of material. Those are different questions, and the difference is large because stars are not distributed evenly in mass. The initial mass function, the distribution of masses a burst of star formation produces, is steep. For every star born above 8 solar masses, several hundred are born below 1. The most common outcome of star formation, by a wide margin, is a star of about a fifth to a third of the Sun's mass, a red dwarf, spectral class M, with a surface temperature under 4,000 Kelvin and a luminosity often less than 1% of the Sun's. The consequences are worth spelling out carefully. In terms of raw counts, something like 3 out of every 4 stars in the Milky Way are M dwarfs. Not one of them is visible to the unaided eye from Earth. Not a single one. The nearest star to the Sun, Proxima Centauri, is an M dwarf at 4.2 light years, and it requires a telescope. So there are 2 different ledgers, and they give different looking answers to the same question. By mass, the universe made half of everything before it was 5 billion years old. By count, the answer is similar in shape, but weighted differently, because the mass function may vary somewhat with metallicity and epoch, and because low mass stars, once made, essentially never leave the count. Here's the thing worth saying plainly. When astronomers say the universe has made most of its stars, they mean it in the mass sense, and they mean it as a statement about a rate that has been measured, integrated, and cross-checked. It is not a poetic claim about the sky feeling old. It is a bookkeeping result, and it is one of the most thoroughly tested bookkeeping results in the field. The dominance of small stars produces a strange split between what exists and what you see. Consider the stars visible to the unaided eye on a clear, dark night, roughly 6,000 of them across the whole sky, about 3,000 at any one time. Almost every single one is intrinsically far brighter than the sun. The ones that look brightest are mostly not the closest. They are the ones that are enormously luminous and merely far away. Rigel, in Orion's foot, is about 860 light-years distant and radiates something like 120,000 times the sun's output. Deneb, in Cygnus, is farther still and brighter still. Meanwhile, the actual population of the solar neighborhood is nothing like that. Of the 50 or so stars within about 16 light years, the large majority are red dwarfs. There is one bright white star, Sirius, and a handful of sun-like stars, and everything else is small and dim. So the naked eye sky is a catalog of exceptions. It shows you the rarest and most luminous objects, selected precisely because they are rare and luminous, and it hides the ordinary population entirely. This distinction matters for tonight's argument because it explains a genuine subtlety. The universe's output of starlight and its output of stellar mass are not the same curve. Massive stars dominate the light and are a small fraction of the mass. Low-mass stars dominate the mass and count and contribute almost nothing to the light. When star formation was 9 times higher, the sky was more than 9 times brighter in the ultraviolet, because the extra star formation produced a disproportionate number of the hot, luminous, short-lived stars that dominate that band. The decline in star formation is therefore an even steeper decline in the visible drama of the universe than it is in the accumulation of mass. Put another way, what has fallen most is not the number of stars being made. It is the brightness of what is being made. The universe still produces red dwarfs at a respectable clip. It produces far fewer of the enormous, brilliant, short-lived stars that made the early universe look the way it did. Which brings us to lifetimes, and to the number that reframes the entire episode. A star's lifetime depends on its mass in a brutally nonlinear way. The fuel available scales roughly with mass. The rate of consumption scales with something like the third or fourth power of mass. Divide one by the other and lifetime scales inversely with mass squared or cubed. Work through the range. A star of 60 solar masses lives about 3 million years. A star of 20 solar masses about 10 million. A star of 5 solar masses about 100 million. The Sun at 1 solar mass has a main sequence lifetime of about 10 billion years, of which roughly 4.6 billion have elapsed. Now go below the Sun and the numbers become difficult to hold. A star of half a solar mass lives for something in the range of 50 to 80 billion years, already several times the current age of the universe. A star of a quarter of a solar mass lives for hundreds of billions. And at the very bottom of the range, at about a tenth of a solar mass, just above the threshold where hydrogen fusion can be sustained at all, the estimated lifetime is of order 10 trillion years. 10 trillion. 10 to the 13th years, roughly 1,000 times the present age of the universe. The reason is not just that these stars are frugal. It is that they are fully convective. In the Sun, only the outer third circulates. The helium produced in the core stays in the core and gradually poisons the reaction. In a red dwarf, the entire star overturns, so hydrogen from the outer layers is continuously carried down into the burning region, and helium is carried out. The star can consume nearly its whole hydrogen supply instead of the 10% or so available to the Sun. It is a slower engine with access to all of its fuel. Here is the consequence, and it is the one that matters. Not a single red dwarf ever formed has died. Not one. In the entire history of the universe, no star below about 80% of the Sun's mass has had time to exhaust its hydrogen. Every one of them that has ever ignited is still burning right now, including the very first ones, formed more than 13 billion years ago. The universe is currently building stars at about 1/9 the rate it managed at its peak, but it has not yet retired the majority of a single generation. Put those two facts side by side, and you get the central paradox of tonight. The universe has already made most of its stars, and almost every star it has ever made is still shining. Both statements are true simultaneously, and together they describe a situation with no everyday analog. We are used to production and decay running at comparable rates, a population where things are made and things wear out, reaching some balance. This is not that. The making has largely finished. The wearing out has barely started. Run the accounting. Of all the stars ever formed, the ones that have died are the massive ones, everything above about 8 solar masses that ended as a supernova, plus everything between about 1 and 8 solar masses old enough to have become a white dwarf. By mass, that is a substantial fraction, roughly a quarter of everything ever formed, returned to the gas. By count, it is a small minority, because massive stars are rare. The great majority of stars ever born are low mass, and the great majority of those are still on the main sequence, doing exactly what they were doing 1 billion years ago, and will still be doing it 100 billion years from now. So the night sky is not a snapshot of a process in progress. It is closer to an archive. What you are looking at is a nearly complete collection of everything the universe built, most of it assembled long ago, almost none of it yet removed. The bright stars in it are recent additions and temporary ones. Rigel and Deneb will be gone in a few million years, and nothing will replace them at the rate the early universe managed. The dim ones, the ones you cannot see, are the permanent collection. There is a version of this that sounds melancholy. The factory is closing. The lights are dimming. Everything is in its late afternoon. But the inventory tells a different story. Nothing has been lost. The overwhelming majority of everything the universe ever made is still here, still burning, and will outlast by an enormous margin every process currently observable. The universe did not run down. It finished building, and then it stopped tearing down at the same time. There is a measurement that captures the difference between mass and light directly, and it is one of the more elegant things anyone has done in observational cosmology. Every photon ever emitted by every star that has ever existed, minus the fraction absorbed and re-emitted by dust, minus the fraction absorbed by intervening gas, is still traveling. It has been reshifted by the expansion of the universe, spread out and diluted, but it has not been destroyed. Added together across all of cosmic history, it forms a faint uniform glow filling all of space at optical and infrared wavelengths called the extragalactic background light. Measuring it is difficult because the foreground contamination is severe. Zodiacal light from dust in our own solar system alone outshines it by a large factor. But it can be inferred indirectly. Very high energy gamma rays from distant blazars interact with background light photons on their way to us and are absorbed. So the observed attenuation of gamma ray spectra as a function of distance gives a measurement of how much background light is out there. The answer is consistent with the star formation history. When you integrate the fitted curve forward, accounting for redshift and for dust reprocessing, you predict a background intensity that matches what the gamma ray absorption implies. Another independent check from an entirely different branch of physics landing in the same place. And what it tells you is that the accumulated light of the universe is dominated by emission from the peak era. The photons filling space tonight were mostly emitted between 8 and 11 billion years ago by galaxies that no longer look anything like they did. There is something worth sitting with in that. The light bathing you right now, the faint uniform glow that permeates every cubic centimeter of the room you're in, is mostly the output of an era that ended before the Earth formed. You are inside the afterglow of cosmic noon. It is far too faint to see, but it is there, arriving continuously from every direction, and it always will be. The stars themselves keep records, and reading them provides yet another independent check on the curve. There are several ways to date a star. For clusters, the classic method is the main sequence turnoff. In a group of stars all born at the same time, the massive ones die first. So the point on the temperature luminosity diagram where stars begin to leave the main sequence move steadily toward lower masses with age. Measure where the turnoff sits and you have the cluster's age, with an accuracy of maybe 10%. For individual stars, there are other approaches. Astroseismology measures oscillations in a star's surface caused by sound waves in its interior. And because those waves depend on the interior structure, they constrain the star's age. Radioactive dating works for a small number of stars with measurable thorium or uranium lines, using the same logic as dating a rock. And white dwarfs cool at a predictable rate once fusion stops. So the temperature of the coldest white dwarfs in a population is a clock that reads how long ago that population formed. Apply these methods to our galaxy, and you get a history. The oldest globular clusters come out at 12 to 13 billion years, forming within the first billion or two after the Big Bang. The thick disk dates to 10 to 12 billion years. The thin disk we live in has been forming stars continuously for perhaps 8 or 9 billion years at a declining rate. That is the cosmic curve, rendered locally, measured with completely different tools than the ones used for distant galaxies. No redshifts, no luminosity functions, no dust corrections applied to unresolved smears of light. Just individual stars in our own neighborhood, dated one at a time, producing a history with the same shape. This kind of cross-check is what turns a plausible reconstruction into a settled result. The distant galaxy surveys and the local stellar archaeology are subject to entirely different systematic errors. When they agree, the thing they agree about is probably real. There is one more agreement worth describing, because it uses the deaths of stars rather than their births. If you know the star formation rate and you assume an initial mass function, you can predict how many stars per unit time cross above 8 solar masses, live briefly, and explode as core collapse supernovae. The conversion works out to about 0.0068 supernova per solar mass of stars formed for the standard mass function. Multiply the star formation rate density by that number, and you have a predicted cosmic supernova rate at every redshift. Then go count supernovae. Repeated deep imaging surveys find them by looking for points of light that appear where nothing was before, and with enough sky coverage and enough repetition, you can measure a rate per unit volume per unit time. The predicted rate and the measured rate agree reasonably well from redshift 0 out to redshift 1, where the data are good. What makes this check particularly valuable is that the assumption about the initial mass function largely cancels out. The star formation rate is derived from the light of massive stars. The supernova rate is produced by massive stars. Both scale with the same part of the mass distribution. So if your assumption about the ratio of massive to low mass stars is wrong, both numbers shift together, and the comparison still works. It tests the shape of the history without depending on the most uncertain assumption in the field. So the ledger has now been checked 4 separate ways. The integrated rate matches the measured stellar mass. The distant galaxy history matches the ages of nearby stars. The predicted supernova rate matches the observed one, and the integrated light matches the gamma ray absorption measurements. 4 different measurements, 4 different sets of instruments, 4 different failure modes, converging on the same curve. That convergence is why this is stated as a result rather than as a hypothesis. It is possible to build a wrong picture that satisfies one test. It is extremely difficult to build one that satisfies four, which is not the same as saying it is finished, and the people who assembled the curve are the first to say so. The largest remaining uncertainty is the one already named, the initial mass function. Everything converts through it. If star formation in the dense, turbulent, metal-poor conditions of the early universe produced systematically more massive stars than it does today, a possibility that is physically motivated, since the fragmentation of a collapsing cloud depends on how efficiently it can cool, and cooling depends on the presence of heavy elements, then the ultraviolet light we measure from that era corresponds to less total stellar mass than we assume, and the peak would be lower than we have drawn it. Second, the faint end. Every luminosity function has to be extrapolated below the survey limit, and the amount of star formation hiding in galaxies too faint to detect is genuinely uncertain, particularly at high redshift, where only the brightest objects are accessible. If there are many more faint star-forming galaxies than assumed, the early part of the curve rises. Third, dust. The infrared corrections are largest exactly where they matter most. Far infrared observatories have coarse angular resolution, which means individual sources blend together at the faint end, and the total obscured star formation at redshifts well above 2 is constrained mainly by the brightest and rarest objects. The honest summary from the review itself is that even with all the current data, it is still hard to pin down the redshift of maximum star formation within a redshift interval of 1. That is a wide window. It corresponds to more than 1 billion years of cosmic time. And there is one more caveat worth stating. Different published fits disagree at the level of tens of percent. The function we have been using produces about 20% fewer stars by the present day than a well-known alternative fit, and reaches its peak at slightly higher redshift with a lower maximum. 20% at the level of an integrated cosmic total is a real difference. None of these uncertainties threaten the conclusion. They move the peak by 1 billion years, or change the total by 1/5, or adjust the steepness of the fall. They do not turn a decline into a rise. Every version of the curve that anyone has published from any group using any tracer agrees that the maximum is far in the past and the present rate is a small fraction of it. The place where the picture has genuinely shifted recently is at the very beginning of the curve, and it happened after that review was written. Beginning in 2022, the James Webb Space Telescope started returning deep infrared imaging of the early universe, the wavelength range where the ultraviolet light of the first galaxies, stretched by a factor of 10 or more, actually arrives. The results at redshifts above 10 were not what most models predicted. There appear to be more bright galaxies at those epochs than expected, and some of them appear more massive or more efficient at converting gas into light than pre-launch models allowed. The community response has been appropriately careful. Several explanations are on the table, and none has clearly won. The earliest galaxies may have formed stars in short, intense bursts, which raises their peak brightness without raising their average mass. They may have contained less dust than assumed. They may have had a different initial mass function, top-heavy in a way that produces more light per unit mass. Or star formation may simply have been more efficient in the smaller, denser halos of that era. Whichever it is, notice what part of the curve this touches. It touches the rise at redshifts above 8, where the total star formation is a small fraction of the cosmic total, and where the review already told us that less than 1% of today's stellar mass was assembled. It does not touch the peak. It does not touch the decline. Nothing found in the last several years has suggested that cosmic noon happened later than we thought, or that the rate today is higher than measured, or that the fall since Redshift 2 is smaller than it appears. The revision underway concerns how the universe got started, not how it has been ending. That distinction is worth being precise about, because the headlines around early universe results tend to imply that everything is being rewritten. The beginning of the story is being rewritten. The middle and the end are holding. So what happens next? For that, go back to the shape of the decline itself. Below Redshift 1, the star formation rate density falls as a simple exponential in cosmic time, with an e-folding timescale of 3.9 billion years. That single number contains the whole future, and it is worth unfolding carefully. An e-folding time of 3.9 billion years means that every 3.9 billion years, the rate drops to about 37% of its previous value. Not by subtraction, by multiplication. Start now. In 3.9 billion years, the rate is about a third of today's. In 7.8 billion, about an eighth. In 11.7 billion, about a 20th. Push out to 39 billion years from now, 10 e-folding times, and the rate is about 1 part in 22,000 of today's, which is roughly 1 part in 200,000 of the peak. Extend it further and the numbers stop meaning much. At 100 billion years, the exponential gives a rate so small that describing it as star formation stretches the word. But the mathematics of an exponential never reaches 0. It only ever reaches smaller. That is the difference between a decline and an ending. And it is why the honest answer to when does the universe stop making stars is not a date. The exponential does not stop. What stops it is a physical limit that the exponential itself does not know about. Eventually, the gas is genuinely gone, locked into low-mass stars and stellar remnants that will not release it on any relevant timescale. And at that point, the process ends for a reason having nothing to do with the fitted curve. There is also a serious question about whether the exponential is the right extrapolation at all. It was fit to data below Redshift 1, covering the last 8 billion years. Using it to predict the next 100 billion is an extrapolation by a factor of more than 10 beyond the range where it was tested. That is not a scientific prediction. It is an illustration of a trend. The trend is worth illustrating anyway, because it makes the direction unmistakable. Whatever the exact form, the universe is heading toward a state in which star formation is not merely reduced but negligible, and it will spend far more of its future in that state than it has spent in all of its history so far. Which brings us to the most quoted number in this subject, and to the reason it should be handled carefully. The claim, which has circulated widely, is that if the observed decline continues, the universe will only ever produce about 5% more stars than it has already made. It is a striking way to put it, and it comes from extrapolating the star formation history measured by the hydrogen alpha survey we discussed earlier, the one that finds the steepest decline, forward to infinite time and integrating. But take it for what it is. What the survey actually reported is a measurement about the past. Star formation since Redshift 2.2 accounts for about 95% of the stellar mass density observed locally today. That is a measurement. The 5% more figure is a different statement produced by assuming that a fitted decline holds indefinitely and integrating the remaining area under the curve. It is an extrapolation, not a measurement, and it inherits every uncertainty of the fit plus the enormous additional assumption that nothing changes for the rest of time. Use the more conservative curve instead, the compiled ultraviolet plus infrared fit with its shallower decline, and the answer for future star formation comes out larger. Perhaps 10% more, perhaps somewhat above that, depending on exactly how you handle gas recycling and how far you push the integration. So the honest statement is a range with a clear direction. Somewhere between about 5 and 15% of all the stars the universe will ever make have yet to be made. The uncertainty is real, and the conclusion survives it. Whatever the precise figure, the overwhelming majority of the universe's star formation is behind it, and no plausible reading of the data changes that. That is the answer to the question in the title, stated as carefully as the evidence allows. Not the universe is done, not star formation has ended. Something more specific and more interesting. The universe has completed something like 9/10 of all the star making it will ever do, and it did most of that work in the first third of its life so far. That remaining tenth has to come from somewhere, and it will not come from outside. So it is worth asking exactly what fuel is left and where it will be found. The first source is return. When a star dies, it gives back part of itself. A sun-like star spends its last few 100,000 years shedding its outer envelope in a slow wind, leaving a white dwarf behind and returning perhaps 45% of its original mass to the interstellar medium. A star of 8 or more solar masses returns a far larger fraction, explosively, leaving only a neutron star or a black hole. Averaged over a full population, the return fraction is about a quarter to a third of everything ever formed. That return material is not the same as what went in. It is enriched, carrying carbon, nitrogen, oxygen, and iron built in the star's interior. And it is hot, so it must cool before it can collapse again. But it is available, and it has been the dominant source of new star-forming gas in mature galaxies for billions of years already. The problem is that this source shrinks. Return depends on stars dying, and the stars that die are the massive ones, and massive stars are made only by ongoing star formation. As star formation declines, the death rate declines behind it, with a lag of a few 100 million years. Less return means less gas, which means less star formation, which means less return. The loop tightens on itself. The second source is the small amount of accretion that still happens. Even galaxies with hot halos are not perfectly sealed. High-velocity clouds of relatively cool gas fall onto the Milky Way's disk today, delivering perhaps a solar mass or so per year, which is not far from what the galaxy consumes. Some of that material is genuinely new. Some of it is recycled fountain gas coming back down. It is enough to keep the current rate roughly in balance, and it will not persist indefinitely. The third source is mergers, which do not create gas but redistribute it and can compress what exists into a burst. Andromeda and the Milky Way will merge in roughly 4 to 5 billion years, and the encounter will likely trigger a final substantial episode of star formation in both, using much of the cold gas either galaxy still holds. That event is on the calendar. It is one of the last large-scale construction projects the local group has scheduled. After that, the arithmetic gets thin. There is one class of object that will keep making stars long after the large galaxies have finished, and it is the least impressive class in the catalog. Dwarf galaxies, systems of a few million to a few billion solar masses, hundreds of times smaller than the Milky Way, behave differently from their larger neighbors in ways that matter here. Their halos are too low in mass to shock heat and falling gas into a stable hot atmosphere, so cold accretion never fully shuts off. Their gravitational wells are shallow, so supernova feedback ejects gas easily, which makes them extremely inefficient at converting what they have. And their star formation is bursty rather than steady, flaring when gas accumulates and pausing while it recovers. The net effect is a system that stretches its fuel over an enormous span of time. Many nearby dwarf irregular galaxies still contain a large fraction of their original gas after 13 billion years, having converted only a small percentage of it into stars. They are the tortoises of this story. Slow, small, and still going long after faster systems have stopped. There are a great many of them. Dwarf galaxies outnumber large ones by a wide margin, and although each contributes little to the cosmic total, collectively they will be the last places where the process continues in any organized way. There is also a smaller and stranger category. In the outskirts of large galaxies, in tidal streams, in gas stripped out during interactions, isolated pockets of star formation appear in places with no proper galaxy at all. A few dozen stars condensing out of a filament of debris, hundreds of thousands of light years from anything. These will persist for as long as there is cold gas anywhere. So the tail of the curve is not a smooth universal fade. It is a scattering of increasingly isolated, increasingly rare sites in increasingly small systems, separated by increasingly enormous distances, each converting a modest amount of gas at a leisurely pace. The cosmic average declines exponentially. The individual events remain the same size they always were. There are simply fewer and fewer of them. Eventually, there is one last one. Somewhere, at some time, the final star of the universe's stelliferous era will begin to collapse out of the final available cloud, and there will be nothing after it. Nobody will be in a position to notice. There is one more reason the gas runs out, and it is the most permanent of all. A large fraction of what has been consumed is never coming back. Every star that has ever formed has locked up material. Some of it will be returned, but three categories of object hold their mass indefinitely. White dwarfs are the remnants of stars below about 8 solar masses, and there are hundreds of billions of them in the Milky Way alone. A white dwarf is a ball of carbon and oxygen about the size of the Earth, held up by electron degeneracy pressure, containing typically 6/10 of a solar mass. It has no fusion, no wind, and no mechanism for returning material. It simply cools over tens of billions of years from a white-hot object to a dim red one, and eventually to something dark. The mass it holds is permanently out of circulation. Neutron stars and black holes are the remnants of the more massive stars, and they retain their mass even more absolutely. And then there are the red dwarfs themselves, which are not remnants at all, but which function the same way for this purpose. A star of a fifth of a solar mass will hold that material for trillions of years before it does anything at all. On any timescale relevant to star formation, gas that goes into a red dwarf is gas that has left the system. Add these together and you get what is sometimes described as a one-way ratchet. Every generation of star formation permanently removes a fraction of the available gas from circulation and returns the rest in a form that is hotter, more enriched, and harder to collapse than what it started with. The reservoir gets smaller with every cycle, not because anything is destroyed, but because more and more of it is tied up in objects that will not release it. This is why the universe's 9% stellar baryon fraction will never climb to anything like 100%. It is not just that the gas is spread too thin or too hot. It is that the process which consumes gas also progressively sequesters it, and the sequestration is essentially permanent. The universe is currently building stars at about 1/9 the rate it managed at its peak, and every star it builds makes the next one slightly harder to build. Which raises the natural question of how long this goes on, and the answer requires a change of units. The physicists who have worked most carefully on the far future divide it into eras. The one we are in is called the stelliferous era, the star-filled era, the period during which conventional star formation continues and the universe is lit by fusion. We are early in it. The universe is 13.8 billion years old, which is about 10 to the 10th years. The stelliferous era is expected to end when the universe is of order 10 to the 14th years old, roughly 1,000 times its present age. Take a moment to place that. If the entire stelliferous era were compressed into a single year, the whole history of the universe so far, everything from the Big Bang through the formation of galaxies, cosmic noon, the birth of the sun, the origin of life on Earth, and every event in human history, would occupy the first 8 hours or so of January the 1st. We are not living in the late stages of anything. We are living in the first morning. But there is a distinction that matters, and it is the one this whole episode has been building toward. The stelliferous era lasts another 10 to the 14th years, not because star formation continues at anything like the current rate for that span, but because the last stars formed will burn for that long. Red dwarfs made today, and red dwarfs made 100 billion years from now out of the last available gas, will still be fusing hydrogen when the universe is thousands of times older than it is now. So the era of star formation and the era of starlight come apart. Star formation, by any measurement we can make, is in its final 10th. Starlight has barely begun. At the end, when the last red dwarf finally exhausts its hydrogen and cools, the universe passes into what is called the degenerate era, a period lasting until something like 10 to the 30 to 7th years, populated by white dwarfs, neutron stars, black holes, and the cold remains of planets, with no fusion anywhere. That is the actual future, as far as anyone can currently model it. Not a dramatic ending. A very long, very slow dimming in which the sky empties one star at a time over a span so much longer than everything that came before that the entire history we have been discussing tonight is a brief opening chapter. There is a consequence of the accelerating expansion that turns this from an abstract projection into something almost personal, and it concerns what will be knowable. Right now, the observable universe contains on the order of hundreds of billions of galaxies. Their light reaches us, carrying redshifts that can be measured, and from those redshifts we reconstructed everything discussed tonight. The rise, the peak, the decline, the whole history. Every piece of that reconstruction depends on being able to look at distant galaxies and read their light. Accelerating expansion is steadily removing that ability. As the expansion accelerates, galaxies not gravitationally bound to us recede faster and faster, their light redshifted further and further, until eventually the wavelengths stretch beyond any possibility of detection, and the objects cross a horizon past which no signal can ever arrive. This is already happening. It simply takes an enormous amount of time to complete. In roughly 100 billion to 200 billion years, everything outside the local group, which by then will have merged into a single large elliptical galaxy, sometimes called Milky Way, will have passed beyond reach. The cosmic microwave background will have been redshifted into undetectability as well. An astronomer working in that era, on a planet around some late red dwarf in that merged galaxy, would look out and see one galaxy in an apparently static void. No other galaxies. No redshift distance relation to measure, because there would be nothing at a distance to measure. No cosmic microwave background. No evidence of expansion. No evidence of a Big Bang. No evidence that the universe had ever been anything other than what it appears to be. They would be able to do excellent local astronomy. They would map their own galaxy in detail, understand stellar evolution completely, and find nothing wrong with their physics. And they would have no way of discovering that they lived in an expanding universe with a hot, dense beginning and a star formation history that peaked long ago. That information will have left the room, which places our own moment in an unusual light. We can see the decline because we happen to live at a time when the evidence for it is still arriving. The observation window that lets a species reconstruct cosmic history is open now. It closes. It is worth being precise about how unusual that is. The stelliferous era runs for something like 10 to the 14th years. The period during which other galaxies remain visible from inside the local group is on the order of 10 to the 11th. So the window in which the history of cosmic star formation can be measured at all occupies roughly 1,000th of the era in which there are stars to measure it from, and we are inside the earliest part of that window rather than the end of it. The evidence has never been more available than it is now, and from here it only becomes harder to collect. So here is where all of this leaves an observer sitting on a small planet, orbiting an ordinary star on the falling limb of the curve. Step outside tonight and look up. What is in front of you is not a process. It is a result. The stars overhead were, with very few exceptions, made a long time ago out of gas that had already been recycled through earlier generations, in an era when the universe was doing this far more vigorously than it does now. They are not being replaced at the rate they were made. When Betelgeuse explodes, sometime in the next 100,000 years, give or take, the universe will not produce another star of that mass in this neighborhood anytime soon. The sky is losing its brightest members faster than it is gaining them. And yet, almost nothing has actually been lost. The overwhelming majority of every star ever formed across all of cosmic history is still burning right now. The population is nearly complete. What has changed is not the inventory, but the rate of addition, and the rate of addition has fallen to about a ninth of what it was. There is a particular kind of quiet in knowing that. Not the quiet of an ending. Nothing is ending on any timescale that would matter to anyone. The quiet of a completed thing. The universe spent the first third of its life so far assembling nearly everything you can see, and it has spent the time since holding on to it. You are looking at an archive that is still lit, the light arriving at your eye from a star 2,000 light years away, left before there were cities on this continent. The atoms in that star were forged in something older still. The gas those atoms came from was assembled in a galaxy that was doing its work when the Earth did not exist. Every layer of it predates every layer of you, and all of it is still going, and will still be going long after the question of who was watching has stopped being asked. That is what a night sky is, not construction, not decay. Something finished, kept, and still burning. Let's gather what we have covered. Because it has been a long way from a single number to a whole cosmic history. We have talked about what it means to measure star formation for an entire universe at once, a rate defined per comoving cubic megaparsec, so that the expansion of space cannot contaminate the answer, currently sitting at 15,000th of a solar mass per year in a box large enough to hold the Milky Way and Andromeda with room to spare. We have talked about the stopwatch that makes the measurement possible. Massive stars, which are enormously luminous, radiate mostly in the ultraviolet and live only about 10 million years, so that any galaxy shining in the far ultraviolet must be making stars right now. We have talked about the dust that hides half the answer, absorbing exactly the ultraviolet photons we depend on, and re-radiating them in the far infrared, so that the real curve is a sum of two books rather than one. And about the strangeness of the fact that the dust obscuring the record was manufactured by the very process the record describes. We have talked about the curve itself, a rise from the first galaxies, scaling as 1 plus redshift to the minus 2.9, a peak at a redshift near 2, when the universe was about 3.5 billion years old, and a decline ever since, following an exponential with an e-folding timescale of 3. 9 billion years. We have talked about the four numbers in the fitting function, 0.015, 2.7, 2.9, and 5. 6 that compress the entire star-making history of the universe into a single line of algebra, and about what happens when you evaluate it. A peak of 0, 133 solar masses per year per cubic megaparsec against 0. 150 today. We've talked about cosmic noon. When a galaxy of the Milky Way's mass packed into a fraction of its volume, half of it still gas, broken into billion solar mass clumps, was forming stars at 50 to 100 solar masses per year instead of 1 or 2. We have talked about the inventory rather than the rate. Half of all stellar mass already assembled before Redshift 1.3, less than 5 billion years in. A quarter formed before the peak. A quarter formed since Redshift 0.7. Less than 1% during the epoch of reionization. Only 8% for more than 5 billion years ago. We have talked about why the rate fell. The shift from cold streams feeding young galaxies directly to hot halos that seal a massive galaxy off from its own surrounding gas, and the molecular fuel census that shows the cold reservoir peaking around Redshift 1. 5 and falling by a factor of 6 since. We have talked about the other breaks. Supernova feedback that dismantles the clouds that made it, black hole accretion tracking the same rise and fall, and reheating the gas that would otherwise cool, and the simple dilution of a universe in which every distance has tripled since the peak. We have talked about dark energy, and about what it means that the growth of structure has now frozen, that each bound system has received its final allocation of material, and that no large-scale delivery of fresh cold gas will ever arrive again. We have talked about our own galaxy. 1 to 2 solar masses a year, a thick disk formed in a burst more than 10 billion years ago, and a handful of visible construction sites like the cloud below Orion's belt, where the process is still running in the open. We have talked about the initial mass function, and about 3 out of 4 stars in this galaxy being red dwarfs, none of them visible to the unaided eye, so that the sky you can actually see is a catalog of rare exceptions rather than a sample of the population. We have talked about lifetimes. 3 million years for the largest stars, 10 billion for the sun, and something like 10 trillion for a star of a tenth of a solar mass, which is roughly 1,000 times the current age of the universe. And about the consequence, which is that not one red dwarf ever formed has died. We have talked about the extrapolations, carefully labeled. Somewhere between about 5 and 15% of all the stars that will ever exist have yet to be made, with the uncertainty depending on which decline you trust and how far you are willing to push a fit beyond the data that produced it. And we have talked about the far future. The stelliferous era ending around 10 to the 14th years, 1,000 times the present age of the universe, and the horizon closing on everything outside the local group in 100 billion years or so, taking the evidence for all of this with it. So, has the universe already made most of its stars? Yes, by mass, and the ledger is not close. The rate peaked more than 9 billion years ago and has fallen to roughly a ninth of its maximum. Half of all stellar material was in place before the universe finished its first 5 billion years. 3/4 of it was assembled after Redshift 2, but the great majority of that came in the window around the peak. And the recent universe, the last 7 billion years, including everything since the sun formed, has contributed about a quarter. What remains ahead is on the order of a tenth, spread across a future so long that the numbers describing it stop being useful. The construction is not finished. It is finishing in the way a tide finishes, not by stopping, but by going out. And the thing that makes this more than a melancholy accounting is the second half of it. Almost nothing has been lost. The stars that died were the bright, brief, extravagant ones, which have always been a small minority by number. Everything else, the enormous quiet population of small red stars, 3 out of every 4 things in this galaxy, is exactly where it was, doing exactly what it was doing, and will still be there long after every process we have discussed tonight has run its course. The universe made most of its stars a long time ago, and then, remarkably, kept nearly all of them. There is a way of living that this resembles, and it is worth naming before we finish. Most of what makes up a life is assembled early and unevenly. The decisive years are not distributed smoothly across a lifetime. There are periods when a great deal is built quickly, and long stretches afterward in which the rate of new construction drops, and the work becomes tending rather than making. It is easy to read that as loss. The more accurate reading is the one the universe demonstrates. The slowing of construction is not the same as the disappearance of what was built. The person you were at 20 is not gone because you are no longer building at that pace. The house is not less of a house because the scaffolding came down. You live in the same condition as the sky above you. Most of your material was assembled before you had any say in it. The rate at which new things are added has slowed and will keep slowing, and essentially all of it is still here, still working, and will keep working for far longer than the era that produced it. Half of every star that exists tonight was already burning before the universe was 5 billion years old. Look at that sky the way you would look at something already complete. The bright ones will go. The dim ones will not. The gas is running low and has been running low for 9 billion years and will keep running low for 100 billion more. Nothing is in a hurry. The rate is 1/9 of what it was. The archive is nearly full. The lights are still on. Good night.